So for the geometry of sulfur dichloride between those two elements, this is a clear-cut case where one is directly to the right of the other, so the chlorine should be more electronegative. It has one proton more than the sulfur and a very similar amount of shielding. Anyway, the electronegativities should be given to you on the exam. So you want to put the less electronegative element in the center. Count up the valence electrons. Subtract the number we've already used, so we've got 16 left. So we put them around the more electronegative atoms first. That's 12. So I've got 4 left. So I have to put them on the sulfur. If I still had more electrons, I would still continue to put them on the sulfur. But I don't. If the sulfur didn't have 8, I would have maybe to consider the chlorine sharing more electrons with the sulfur to make its noble gas configuration. But it does have 8 already, so I don't really need to do anything about that. I should then calculate the formal charge for any of the atoms. So the chlorine has 7 that it needs to be balanced. I can assign 6 from the lone pairs and half of the 2 that it's sharing with the sulfur. So that's neutral for both chlorines. For the sulfur, it only needs 6 to be neutral because it's in column 6A. So I'd subtract from that the 4 electrons that it has, 1, 2, 3, 4, in its lone pair that it has all to itself. And then half of the 4 that it's sharing with the chlorines on either side. That's also 0. So that suggests that the molecule should be pretty stable. All the atoms have noble gas configurations. There's no formal charge. So today we're going to talk about polarity, and we're going to see how the polarity of the molecule will affect the types of interactions it can have with other molecules, which is a big part of predicting the types of properties it will express as a macroscopic sample. So in order to analyze its polarity, we need to first look at its geometry, and that requires us to focus in on the central atom to look at how many pairs of electrons there are, or domains of electrons, and a lone pair counts as a domain, a single bond counts as a domain, a double or triple bond counts as one domain. So in this case the sulfur has 4 domains. So when I think about the way that's going to look, the 4 electron domains are going to have a tetrahedral geometry spread out with angles of about 109. And so that means if the angles are all 109, the 2 chlorines have to have about that angle. So I could write it like that. I could write it like this. Either way, I realize that when the lone pairs are there, they're occupying some of the 2 of the 4 spots in that tetrahedral type shape. So then I have to look at the molecular geometry, which is just what is the shape created by the atoms. And that would be bent. So in this one, this formula is a little bit different, right? This formula, there's 2 carbons, 2 hydrogens, and 2 oxygens. So this way of writing the formula just tells you how many atoms of each type there are. If you see a formula like this, it also gives you structural information. It's telling you that 3 of these hydrogens are on this 1 carbon. So when I'm writing the Lewis structure, I've got a guide there that helps me do that. And the next carbon has 2 oxygens and a hydrogen. So this type of condensed structural formula doesn't really tell me for sure if the hydrogen is here or if it's on one of these oxygens. So that might require a little trial and error. If I put it here and I put the remaining electrons in, there won't be enough to give this oxygen 8 once I count up the total number. So that means I've got to move this hydrogen here. Now the element that doesn't have 8 is the carbon, which only has 6. but that's okay because it's bonded directly to an atom with a lone pair that can be shared in there. So that means this carbon here will be tetrahedral because it's got 4 electron domains and they're all bonds. So all 4 bonds are spread out of tetrahedral geometry. This carbon here is trigonal because it only has 3 atoms attached to it. But since it doesn't have a lone pair, it's trigonal planar. All of the 3 electron domains are in the same plane and they're all connected to atoms or bonds. The oxygen is going to be bent just like the sulfur for the same reason, because of the 2 lone pairs. Because the electron domain geometry is tetrahedral, only 2 of those electron domains are actually connected to atoms, so they have to be connected at that angle that's close to 109 that you get for the tetrahedral electron domain geometry.